In this video, we're going to review the material that we'd seen in class on polar coordinates and polar curves before our semester was suspended for 2 weeks. So we'd seen polar coordinates as opposed to rectangular coordinates. So polar and rectangular coordinates, let's just remember what these are. Rectangular coordinates are the typical xy coordinates that you are used to using. Cartesian coordinates is another name. And they're called rectangular coordinates because the x and the y are two sides of the rectangle, which determines the position of the point. Polar coordinates are called polar. Well, that's actually a really good reason. I'm not sure why they're called polar. I should look that up. But they determine the same point with two different measures. They determine it with the distance from the origin, that is called r, and the angle that the r, the radius r, theta, makes with the positive x-axis. So just like in your trigonometry from high school. And so the way that x and y correspond to r and theta is through this set of trigonometric and Pythagorean identities. So these formulas help us go back and forth from rectangular to polar and vice versa. So we had also talked about switching coordinates, but for us now going forward, the most important is going to be switching really from rectangular to polar. We practiced in class going the other way as well. That's going to be less important. So let's just review going from rectangular to polar. So for an example here, we're going to substitute. The way we go from rectangular to polar is by substituting those formulas above, the formulas right here. So if we want to change the curve y is equal to root 3x into polar coordinates, where we're going to use y as r sine theta, x as r cos theta, and then go ahead and do some simplification. So there's two possibilities. Obviously, either r could be 0, in which case both sides are 0, or if r is non-zero, then you get sine over cos is root 3, which means tan is root 3, or theta is pi over 3. So what does that tell us? That tells us in rectangular coordinates, the line y is equal to root 3x can be described exactly the same. It's the same line. It's just a different way of almost spelling it, right? You're using a different set of coordinates, r and theta. The r actually disappears in this one, except for r equals 0. That's what lets us have the origin there. Theta is equal to pi over 3. Tells us exactly the same line as y is equal to root 3x. We had also seen graphing in polar coordinates. And so we had looked at the idea here of polar graph paper. Polar graph paper. And polar graph paper has grid lines that aren't grids. They're not rectangles. They are based, instead of on x and y, they are based on r and theta. And so the circles around the origin are circles where r is some value of k, a constant. And what I've got as dotted lines here coming out from the origin is theta, is c, some constant as well. So we looked at plotting these kinds of points, and so the little example that I've got here for us is asking us to plot first point A where the radius is 2 and the theta is pi over 4. And so that's really simple. On a graph like this, you're going to go to where the angle theta is pi over 4, and then you're going to look up, right, from the origin a radial distance of 1, 2. Right, whoops. Right, so 2 units there's our radius of 2 along the dotted line where theta is pi over 4. So that gives us point A. Point B I've chosen here to demonstrate what happens when you've got a negative radius. So when r is minus 3 and theta is 11 pi over 6. So 11 pi over 6, well, that's coterminal with theta, often written theta bar, coterminal angle, is negative pi over 6. So that's an angle here. Theta is 11 pi over 6. So we're going to be somewhere along this theta line here. And so if r is negative, instead of coming out 1, 2, 3, so instead of coming out in this direction, right, that would be the positive radius direction. Since our theta is negative, we're going to be going out in the opposite direction, but along the same dotted line. So we're going to be going 1, 2, 3, and it looks like I put B in the wrong place when I was preparing this. So B actually should go here 3, right? That is our point B right here. So there's B. I'd actually drawn B as if it were negative 4. So there's B. Okay, next, polar plots. So what had we seen in terms of graphing things more than points? The first thing that we had looked at, or that I had mentioned, was that r is f of theta. That is the usual form of a function. R is typically written as a function of theta. So theta is the independent variable and r is usually the dependent variable. So what we have below are plots that we did in class, and the ones that are marked with a asterisk here are ones that I expect you to know, just to know by heart. But I could ask you to figure out another plot, with a table of values, or plotting like we did in class by looking at the function, a graph of the function and determining the radius, and using those techniques. You could be asked to plot other things. But those things marked with an asterisk are things that I'm going to just assume that you know. And so let's just go through and highlight all those asterisks right here. These are the functions, the graphs. We'll go through them one by one in a second, that I expect you to know. The ones that don't have asterisks, right? These we did in class. It's good for you to know kind of that they exist, that they what they look like, right? They might come up. I might call something a rose or a cardioid. Actually, I see that word is missing, so let's put that there. Whoops. This is a cardioid, right? But you don't actually have to memorize the graphs and how to graph those. So let's go through these guys in order. The first is probably the simplest kind of graph. R is a constant, right? And in rectangular coordinates, this circle would have x squared plus y squared is equal to a squared. So here r is equal to a. Typically a is given as greater than, I guess it could be equal to, greater than or equal to 0, but it doesn't actually need to be. If you drew r is -7 or whatever, you would actually get the same circle as if you drew r is equal to 7, because of what we said previously, that negative radiuses just go on the other side. But everything is perfectly symmetric here, so you would in fact get the same circle. So the graph of r is equal to a. Let's choose another pretty color here. Orange, how about that? The graph of r is equal to a is a circle with radius absolute value of a, and it's centered at the origin. We'd graphed two other kinds of circles. One of this form. I don't think we'd given the general form in class, but here it is. R is 2a times sine theta. That again is a circle with radius absolute value of a, but this time it's not centered at the origin. It's centered at the point 0a, and I'm giving those in rectangular coordinates. Right here's the center of the circle right there. And if it's radius a, that means it goes from 0 down here at the bottom up to 2a. Right? So radius A, centered at A, that's what you get. Next is the curve r is equal to 2a cos theta. Very, very similar. It's a circle, radius, absolute value of a, but this time it's centered on the x-axis. It's centered at a0, and so you get the same idea, but along the x-axis. So here you have a, here you have 2a, and then the total radius, right? The radius of that circle, so that's a radius. That value is a, but that value, that radius, is the same anywhere. We had seen theta is equal to a constant. We'd just seen that earlier with our pi over 3 example. That is a line through the origin, that corresponds to the angle theta that's being made with the positive x-axis. I had you figure out as well, r is a secant theta. That is a vertical line, x equals a. Right? So a secant theta described in polar coordinates is the same line as x equals a described in rectangular coordinates. Okay, that's the end of the ones that I'm going to assume that you know, but we did see the cardioid. The equation of the cardioid was this. I mean, it's important that you sort of recognize the form of a cardioid. I might use the word, but if I do, I'll give you the equation. And the same thing for the rose, right? The rose, there's many different kinds of roses. They can be written with cosine, they can be written with sine, and different properties about this number here and how many petals you get. These things are called the petals of the rose. And there are properties there that we're just not going to get into. What I just want to make sure that you're aware of is the existence of these lovely curves, cardioids and roses. Okay, guys, and so that's it. We're going to pick up in class or next week with a new material that is going to be based on this, and we're going to go into integration, double integrals that are going to be using polar coordinates for simplification.